Tesla and its competitors in the battery-powered electric vehicle market dominate debate over who will control the future of cars. But there's another kind of green transportation technology making inroads, and it is based on the most abundant resource in the universe. It is fuel cell electric vehicle, or hydrogen car in simple words. FCEV, abbreviation for fuel cell electric vehicles, combine hydrogen stored in a tank with oxygen from the air, to produce electricity to power an electric motor, with water vapor as the byproduct. Unlike more common battery-powered electric vehicles, fuel cell vehicles don't need to be plugged in. They're filled up with a nozzle almost as quickly as traditional gas and diesel vehicles, but we need hydrogen filling stations to feed the cars. There are many commercial FCEV in use since long, and recent past has given us Toyota Mirai, Honda Clarity and Hyundai Nexo, to embellish your own parking space. Now coming to key components of a hydrogen fuel cell electric car. Auxiliary battery. The auxiliary battery provides electricity to start the car before the traction battery is engaged, and also powers vehicle accessories. Then is battery pack. This battery stores energy generated from regenerative braking, and provides supplemental power to the electric traction motor. Then comes DC converter. This device converts higher voltage DC power from the traction battery pack, to the lower voltage DC power, needed to run vehicle accessories, and recharge the auxiliary battery. A fuel cell boost converter is a compact, high-efficiency, high-capacity converter, newly developed to boost fuel cell stack voltage to 650 volts. A boost converter is used to obtain an output with a higher voltage than the input. Then the unique component, fuel cell stack, an assembly of individual membrane electrodes, that use hydrogen and oxygen to produce electricity. In their most basic form, fuel cells contain an anode, cathode, and a polymer electrolyte membrane, BEM. Because each cell generates little voltage on its own, engineers string them together in a series, or a stack. The Mirai's stack contains 370 cells, each working to transform stored chemical energy into electricity. Here's how. In each cell, hydrogen runs through a flow field plate to the anode. There, a platinum-cobalt catalyst splits the hydrogen molecules into positively charged ions, and negatively charged electrons. Then, the PEM permits the hydrogen ions to pass through to the cathode, but it stops electrons, forcing them instead to travel an outer circuit, creating an electric current. Finally, electrons and ions meet up with oxygen at the cathode to form water, which is emitted primarily as vapor. Another key component is power electronics controller. This unit manages the flow of electrical energy delivered by the fuel cell, and the traction battery, controlling the speed of the electric traction motor, and the torque it produces. Now electric traction motor, using power from the fuel cell and the traction battery pack, this motor drives the vehicle's wheels. Some vehicles use motor generators, that perform both the drive and regeneration functions. Then we have fuel filler, a nozzle from a fuel dispenser attaches to the receptacle on the vehicle to fill the tank. Then comes hydrogen fuel tank. It stores hydrogen gas on board the vehicle, X until it's needed by the fuel cell. Before proceeding ahead with other key components, let's know how fuel cell car works, from intake to exhaust. It's new technology and is interesting indeed. There is thermal cooling system. This system maintains a proper operating temperature range of the fuel cell, electric motor, power electronics, and other components. Then comes electric transmission. The transmission transfers mechanical power from the electric traction motor to drive the wheels. A 2017 survey of 1,000 senior auto executives conducted by KPMG found they believe hydrogen fuel cells have a better long-term future than electric cars, and will represent the real breakthrough. David Antonelli, chair of physical chemistry at Lancaster University, has said, "We could see hydrogen fuel cell systems that cost 4 times less than lithium-ion batteries, as well as providing a much longer range. Some are showing safety is a concern, as hydrogen is flammable, but so is gasoline in lithium-ion batteries. Some studies have said of lesser risk with hydrogen, as it rises very fast, being very light in case of minor leaks. The transportation of hydrogen for use at refilling stations poses additional safety risks. Stations use sensors to monitor for leaks. There have not been serious incidents reported in California, area with maximum no of hydrogen filling stations, and the industrial sector has been transporting hydrogen for decades. As of now, technology is costly and availability is scarce, however ongoing developments will ease off these concerns. There has been a tendency for the automotive sector to view battery electric vehicles, BEV, and fuel cell electric vehicles, FCEV, as competing technologies. There are benefits to both fuel technologies. FCEV can offer better weight economy, making them effective when powering larger vehicles such as haulage and courier trucks that need to limit unnecessary weight gain. Vehicles that regularly travel long distances or that need to refuel quickly are also more suited to hydrogen. Hydrogen is also a good choice for longer-term storage, since it is a gas that can easily be stored in tanks and containers, while battery lifetime can suffer if the batteries are not charged and discharged correctly. However, hydrogen's sustainable future largely relies on the production of green hydrogen, produced through electrolysis that's powered by renewable resources like offshore wind. Currently, around 96% of hydrogen is generated from fossil fuels, so developments must still be made if FCEV are going to match the feasibility of BEV. It is a highly attractive alternative to fossil fuels, particularly in sectors where electrification may not prove as effective, such as aviation, shipping, iron and steel production, or long-distance road transportation. Lithium-ion battery production for electric vehicles is very energy-intensive. As an example, a 100 kWh battery will give a potential range of 250 miles and, in order to produce that battery, it will take around 20 tons of CO2. A typical battery lasts for 150,000 miles, so that equates to around 83 grams per km of CO2. Then, when you take into account charging over that same distance, the same battery car will deliver 124 grams per kilometer of CO2 over its lifetime. In comparison, today's hydrogen cars have life cycle emissions that are at least as low. A recent study found a hydrogen car such as the Toyota Mirai emits around 120 grams per kilometer of CO2 over its lifetime. But this can be brought significantly down when hydrogen is produced from renewables, means green hydrogen. With evolving technologies every moment, FCEV tech is not going to replace BEV tech or vice versa but will coexist.